Thank you, Jeff, and thanks everyone for coming here today. I'm going to talk about some stuff that we've been doing at Stanford. I'd like to stress that there's a long list of people who did most of the work. In fact, almost all of it. I did nothing. The students came up with this idea, and they locked me out of the lab for 3 days, and then, this is what we got 2 years later. So I'm going to talk about wireless, but unlike many wireless talks, it's actually going to be pretty math light. I'm only really assume that you maybe know something about the physics of sine waves. I find it usually works better that way. So full duplex wireless. Why is this a big deal? Who cares? So here's an interview with Chuck Thacker, won the Turing Award last year for essentially working on the Alto, part of which was the development of Ethernet. So here's this part of the interview where they ask, hey, so you worked on Ethernet? He says, yeah. And the big insight in Ethernet was, Aloha, which is a packet network developed in Hawaii. Well, these radios, they had this problem, which is they couldn't receive and transmit at the same time. But for Ethernet, you can tell if somebody's transmitting when you're transmitting, and that's how CSMA, collision detection, works on wired networks today, Ethernet. But on radios, you couldn't do it. You couldn't receive and transmit simultaneously. In fact, if you open a wireless textbook today, so here's a textbook by a wonderful colleague of mine, Andrea Goldsmith, RF Communications. You open the textbook, and it says, generally, radios cannot receive and transmit simultaneously on the same frequency. If you want a radio to receive and transmit, you either have to slice it in time, so it alternates between receiving and transmitting. That's what most, say, Wi-Fi does today. Or in frequency, where you receive on one frequency and transmit on the other. That's what, say, a lot of cellular systems do today. But you can't do both simultaneously on a single frequency. So this talk in a nutshell is, actually you can. You can build radios that receive and transmit simultaneously on a single frequency. Some students at Stanford have built working prototypes of doing this up to about Wi-Fi level devices. So 200 milliwatts, 20 megahertz wide wireless signals. I'll talk about why those numbers matter. Basically, the question here is how strong a signal can you transmit full duplex? You can imagine that as you transmit stronger and stronger, it becomes harder and harder to hear what others are saying. So I'm going to talk about how you do it. That's going to be most of the talk, the technical implementation of how you do this. Spend a little bit of time talking about why this matters. So what? You can receive and transmit. And going forward, what are some of the barriers and challenges, sort of deal breakers? What could, in fact, we've done this in the lab, we've done some prototypes, we've done some demonstrations. What are things that might make this, say, impractical in commercial systems? So why is full duplex hard? Why are systems half duplex today? The basic problem is self-interference. So you imagine if a transmitter on the left and it wants to receive a signal from the node on the right, the green signal. Well, because its transmit and receive antennas are very close to each other compared to the distance to the other node's transmit antenna, its own signal is going to be millions to billions times stronger than what it's trying to hear. Essentially, this node on the left is trying to hear a whisper from across the room while it itself is shouting. This is really hard. And so the basic point is, if there's some way we could subtract our own signal, if we could, say, subtract our own shout from what we're hearing, then you could receive and transmit simultaneously. But how do you do that? That's the hard part. That's the basic question. If you can do that, you can have a radio receive and transmit at the same time. So before this work, a bunch of people were playing around in the space trying to do it, using several different techniques, including digital cancellation. So I take these analog waveforms, I turn them into digital values using an ADC, and this is what radios do. And then I can just subtract these digital values, these small integers. Zigzag did this, analog network coding, a lot of work from different places. Another approach is, turns out there are some hardware cancellation circuits out there you could use. When you put on a pair of noise-canceling headphones, there's actually there's an interference cancellation circuit in there. It's taking the sound from outside the headphones, subtracting it from what you're hearing, and then that, in theory, will sort of cancel out the noise from, say, the plane. But in practice, these would give you about 15 dB, 25 dB best case cancellation. And if we want to have a full duplex radio, we need on the order of 70 to 90 dB of cancellation. So these two techniques alone were not enough. Yeah? Decibels. So it's a measure of magnitude. It's a logarithmic scale, so 10 decibels is 10-fold, 100 decibels is 20 decibels is 100-fold, 30 decibels is 1,000-fold. So just a way to measure signal strength. So the first design that students came up with, Mayank, Kanan, and Jung-il, was just ridiculously simple. You have two transmit antennas, and you have one receive antenna. And you place the receive antenna so that it's distance d from one transmit antenna, and d plus half the wavelength from the other one. So now these two waves, offset by half the wavelength, will interfere destructively at the receiver. And so the receiver is at this null position where it hears a much, much weaker signal than anywhere else. And using this technique, it turns out you could get about 30 dB of self-interference cancellation. You could reduce what your own transmitted signal by 1,000-fold, which, when you combine it with all the other stuff, meant that you could build a full duplex radio that would operate at about 1 milliwatt. So think low power wireless, so personal area networks, sensor networks, that kind of stuff. 802.15.4. So,
line of sight, no multipath?
Yes, this is all line of sight. At the end, I'll talk a little bit about multipath. That's one of the like, hey, deal breakers, right? The second design handles some multipath, basically in the digital domain, got some multiple taps. Yeah, this is totally, because that's going to be the principal interference path, right? Especially if, like, literally it is line of sight. So, and so the point is, in this first design, this was in Mobicom last year, you add these three techniques up and you get 70 dB of cancellation, which is about enough to build a full duplex 1 milliwatt transmitter. Kind of neat. It's great. But what's especially kind of neat was just how simple it was. I mean, literally, we've got a software radio there for digital interference cancellation, just so we can implement it. There's the hardware cancellation circuit. And then to configure the antennas like this, there's a wooden board, and it has 3 holes drilled in it. And there are the 3 antennas. So my one part in this is I got to, like, drill the holes in the wooden board. Right? That's what I did. But, like, that's, you just take a wooden board, and you can build a full duplex radio. So this isn't super precise. So bringing it together, the way this radio works is at the top you have this technique called antenna cancellation, right, which is canceling about 30 dB. Then that signal from the receive antenna, which has 30 decibels of your own self-transmission, sort of the power of your own self-transmission has been reduced 1,000-fold. It passed to a hardware cancellation circuit, which can pull out about another 25 dB, reduce the signal by 25 decibels. And then that signal is passed into an analog digital converter, converted into digital values, which then software can use for digital cancellation. And then come out and you get clean RX samples. You can receive a packet from another device, even while you're transmitting at full power. Well, full power here means 1 milliwatt. Great. So that's it, right? We're done. So not really. Why 1 milliwatt? So I'm going to walk through a little bit about these techniques and why I was talking about 1 milliwatt. Then this will sort of lead to why the second technique published this year can do up to 200 milliwatts. So first, let's just look at this antenna cancellation. So we have 2 transmit antennas, TX1 on the left, TX2 on the right. And what I'm showing here on the plot is as we move the receive antenna, this is in that board basically, what is the observed signal strength of the signal? And so as you see, we move the receive antenna further away from TX1, the observed signal strength goes down, just decaying with distance as you'd expect. The same is true when TX2 is active. As we move the receive antenna away from TX2, the signal strength goes down. And where those 2 points cross, you get this notch, this deep null, where now those 2 signal strengths are just about equal, and they're offset by half the wavelength, and so they cancel each other. So you put your receive antenna there, and suddenly what you hear is 1,000th as strong. You're in sort of, it's like you're being in a bad auditorium where there's a dead spot. You position the receive antenna, at the dead spot. Feel free to interrupt me anytime with questions.
So the solution is to have a motor, right? Just move the antenna.
So actually, it turns out no. What you'd really like to do is programmatically, it turns out the distance isn't what matters, it's the delay. And so what you want are programmable delay lines. And that's where this is eventually going. And that's one of the really the technical gotchas, is the precision of your delay lines. Yeah.
How do you synchronize it to the antenna?
Synchronize them. I just take a signal and I split it.
Oh, I see. So
There's no sync.
they come from the same physical source.
Yes. So if anyone's been following this stuff at all, there's another proposal from Rice on how you do this, where they actually use two separate transmit chains. And they generate an inverse signal, and this has issues of introducing noise and things like that.
They have the
Same
same phase.
phase?
Based on their sequence.
Yes, yeah. I mean, it's literally, I guess this picture doesn't show it, but yeah. So it's literally that you just split the transmit signal, right? And then you're controlling the delay.
So you guys and Rice and just about everyone's using the same hardware canceller chip.
Yeah.
And I've heard that it's a finicky
Yes.
equipment.
Yes.
So that it doesn't always behave. The summing it up by saying it gives you 25 dB or whatever, maybe it's a simplification.
That is totally the case. In this particular situation, because it turns out that it took us a long time to actually figure out what that hardware cancellation chip is doing, and it's kind of weird. Where it has some control, you can say control amplitude and control gain. What it's actually doing is it takes your signal, and then it adds a fixed delay copy of the signal, so it's the quadrature signal, and then you control the gain of the main signal and the quadrature to, in theory, generate any delay. But that doesn't actually work, as I'll talk in a second, because that would work for a single frequency, but you're not a single frequency. Yeah, so it's finicky. It's a total approximation widget. It's just something you can buy for cheap, which is why we use it.
So for you, your 20 megahertz baseband on carrier of what? Using 2.4 gigahertz?
Yeah, 2.4 gigahertz. So this is 2.4 gig. This result here is 2.4 gigahertz, 5 megahertz. 5 megahertz wide. This is the low power wireless. The one I'll show later is 20 megahertz, and I'll show why this is 5 megahertz on the next slide, or in the slide after this. So there's this question, right? We want to match these signals at the receive antenna, both in amplitude and then also offset by half the wavelength, So how precise do we have to be? So what these plots show is just simple analytical results for depending what your amplitude mismatch is, depending on how precisely you can match the amplitude of the two waves, and then your placement error, like how precisely you can place the antenna and control the phase that arrives, what's the maximum cancellation you can get? And the basic point from this is that in order to get 30 dB of cancellation, you need about a 0.5 dB accuracy for matching the amplitudes, so about 5%. It's not terrible. And for placement error, it needs to be within a millimeter. So you can move the antenna, you can jiggle it half a millimeter, and you'll be okay. So hence, that's why we could use a wooden board, right? If you needed, a tenth of a millimeter, a wooden board wouldn't have sufficed. So doesn't require tremendous precision to do this. And so this is good enough for 802.15.4, 5 megahertz wide, 1 milliwatt, but if you want to do something at 200 milliwatts, you're going to need something better than this. But that's fine. That's just a question of precision. It turns out that this technique that I'm describing, this phase offset antenna cancellation, has a fundamental bound, in the sense that there is a bound under which no matter how precise your system is, you can't do better. And we call this the bandwidth constraint. It's caused by the fact that a wireless signal is not a single frequency. It has a bandwidth. And so when I said you take the second antenna and you offset it by half the wavelength, well, across the bandwidth of a signal, right, like a Wi-Fi signal is 20 megahertz wide and 802.15.4, like a Zigbee signal is 5 megahertz wide, that half the wavelength can only match one frequency. And so you're basically, if you have a wide signal, the receive antenna can cancel one frequency perfectly, and then the frequencies, as they get further from that center frequency, will not be canceled as well. Their phases won't match exactly. And so in practice, what this means is for something like Wi-Fi, just the fact that the signal is 20 megahertz wide results in, it's as if you can't place the antenna perfectly. It's as if there was a 1/4 of a millimeter placement error. And you can plot just analytically what this bound means. And say for different, depending on what band you're in, 300 megahertz, 2.4 gigahertz, 5.1 gigahertz, depending on what the bandwidth of your signal is, what's the best you could possibly do? You cannot do better than this. And the basic takeaway is that if you want to do like Wi-Fi using phase offset, the best you could possibly do is 47 dB because of the 2.4 gigahertz band, 20 megahertz wide. And so using phase offset, you could maybe just barely, if you got everything perfect, do Wi-Fi, but not quite. Not quite. Okay. So students built it. They built a pair of nodes, had one node fixed, moved the other node around, evaluated them, demoed it at Mobicom last year, and can show you, oh, look, nodes can transmit and receive simultaneously. So on the top, you see half-duplex. The nodes have to alternate. On the bottom, nodes can transmit and receive at the same time. It's great. It's fun. And at the very least, this is neat, right? You double your aggregate throughput. I can receive and transmit simultaneously. Once they did some further evaluations, there's that test setup I showed before, and saw that, yeah, you see a median gain across all the experiments of about 84%. So you're within 92% of the efficiency of a perfect full duplex system, one that actually doubled capacity. And this is, software radios and these little cancellation circuits and, some antennas we've sort of put up on top of a box. So this is not, as good as engineering as you can do in, 3 months with a few graduate students.
So hardware cancer was put before the USRP because the USRP
Yes.
gives you digital out.
Yes. Yes. Yeah. So back there. So first is antenna cancellation, then hardware cancellation, then digital cancellation. Yeah. Great. It turns out that USRPs also have some issues where you get some packet loss at low SNRs because they have some weird gain issues. So I showed you can build a full duplex radio. 802.15.4. And this first prototype, just a couple months of work, can give you an 84% throughput gain compared to a single radio. But this design has a bunch of problems. Number one, we need 3 antennas. If you work in wireless, if I had 3 antennas, I can do 3x3 MIMO. Like, why am I doing this? This seems like a waste of time. Number two, it's limited to 15.4. 5 megahertz wide, 1 milliwatt. There's lots more interesting wireless out there. Limitation 3, the fact that you have these 2 transmit antennas, you're creating a null position at your receive antenna. Now, you don't create null positions in the far field, like far away, but you do create weird signal strength variations because you basically have self-interference out there. You don't create nulls, very deep nulls, because the 2 transmit antennas are different powers, but you do have these weird far field effects. I can show a picture of it later if people are interested. Finally, this is just these manually tuned systems, right? We'd have a little software utility, tweak stuff. It would work for 5 or 6 minutes. You move things around, you need to retweak it. There's no dynamic adaptation to the environment. Yeah?
Why is the gain 1.4 not 2?
1.84. I'm sorry.
It would be double what half-duplex? The 1.4 is throughput gain.
Because it's not perfect.
Yeah, the assumption would be that if it were perfect, we'd double the throughput because we're going to receive and transmit simultaneously. But what we saw is in our design, like, we lose some packets when we're doing this because our cancellation is imperfect. We've got bugs, and we're actually going through all the digital stuff, right? Basically, the engineering is not perfect such that the cancellation has some blips in it. Right. Okay. Great. So, can we do better? And the answer is yes. But so let's go back to that original picture. So why half duplex? I said if only we could subtract our transmission. Right? If we could subtract our own self-transmission, then we could be full duplex. Now, if you think about it, this notion of using 2 signals that are offset in phase, offset in delay, that's really sort of a poor man's subtraction. As the bandwidth constraint showed us, you really only can subtract one frequency, and the others you're mostly subtracting, but as they get further out, you're subtracting them less and less well. And just to show you the picture, right, when you're using phase offset, I have this purple signal right at my center frequency. I offset it by half the phase. It's great. I can cancel that perfectly. But then a signal, say, with a slightly lower frequency is not going to be offset exactly, and so I'll actually get some of the signal out. And so this notion of using phase offset is frequency dependent and only really works for narrowband signals. Now, if instead I could just invert the signal, so I have two copies of the signal, it's plus and it's minus, and let's match them in delay exactly, not offset in time, then it wouldn't matter. There's no difference in phase. Like the phase for every version, you're matching the two signals exactly, but one is just a negative copy of the other. If we did this, then we could get a full duplex transmitter. And so it turns out you can. There's a simple circuit to do this, balanced, unbalanced transformer, a Balun. You put a positive signal in one side, and on the other side you get a positive copy of the signal and a negative copy. So now we have the positive and the negative copies of this signal. So take a traditional radio design where we have this self-interference. We come in some transmit power T. It attenuates over space, and there's some delay. Let's just call it AT. I'm being very fuzzy with the math here. I realize that if you're in RF communications, just to give you a basic idea of what's going on. So the self-interference is that transmitted signal with some delay and some attenuation. And now what your receive antenna is going to hear is this green signal, R, that you want to receive, plus then what you yourself are transmitting, which is generally going to be 90 dB stronger. What you do is you take your transmit signal, and you do have to double its power coming out of the TX front end. You put it through the Balun. The positive copy you transmit. The negative copy you sum with the received signal. So now suddenly what I'm receiving is not just R plus my self-interference. It's R plus my self-interference plus then this, or minus basically this negative copy. So what I want to do is match that negative copy of the signal coming out of the Balun in delay and amplitude to the positive copy that's in my self-interference. So you put in a variable attenuator and delay line, which then takes that minus T, makes it a minus VT, and now suddenly what I'm receiving is R plus my self-interference, then minus this cancellation signal controlled in amplitude and delay. And if I can configure this so that basically V equals A, that the delay and attenuation across that box is the same as over space, then it'll cancel my self-interference and I can recover R. This is the second design. And because we're using signal inversion, there isn't this narrowband limitation. So to evaluate this, we said this is a simple wired setup. So there's the transmitted signal, and we just put it through a Balun, then sum the two copies, and put that to a receive chain. That's for the signal inversion setup. For the phase offset, so antenna cancellation, we put a lambda over 2 delay for the two positive copies. Here's just a simple signal splitter. And we want to measure now what kind of cancellation do we see across the band, so across the entire band we're looking at. Is it that actually this approach is wider band, isn't limited to just one frequency? So we did 2.4 gigahertz, and just to see how wide it was, I did a 240 megahertz chirp. So Wi-Fi is 20 megahertz wide. We're looking at a chirp that's 12 times that. And this is what we saw. So on the left is just showing you for the given frequency, what's the received signal strength at that frequency. And so for phase offset, you can see there's this really deep notch because it only matches one frequency exactly. But using signal inversion, we have a notch. Of course, it's not across the entire band. In theory, you can cancel everything perfectly. In practice, hardware does real stuff. But the basic point is that this notch down at around minus 105 or so, which is actually the noise floor of this circuit, is about 20 megahertz wide. So for this particular Balun we used, we actually could cancel across the entire, this 20 megahertz band. So on the right then shows
The width of that, of the notch at the bottom, is that entirely a function of some aspect of that Balin circuit? Do you get a different one? Is it narrower or wider or what have you? Or is that a kind of fundamental? That notch is going to be that big, period?
So it is not going to be just that big period. It is a function of that Balin circuit. So I think we probably could buy like a better Balin, one that's more precisely engineered, which would be a little wider, or a cheaper one, which would be a little narrower. There's also even where it is, in the sense of, look, this one cancels really well around 2.46. Another one might cancel really well around 2.45. Yeah. So it's not even just the circuit, it's also the particular instance of that circuit, if that makes sense. Yeah. But it's real. I mean, it's not like I'm not going to claim that you can build a Balin that'll do this across 240 megahertz, right? That might, I mean, very well just not be feasible from an engineering standpoint. And so what this means, right, is you actually look at the amount of cancellation you get from signal inversion versus a phase offset over a wider band signal, and signal inversion can cancel much more. And so what that means is that at a 20 megahertz bandwidth, you can cancel about 50 dB using signal inversion. So you get a significant improvement in cancellation. And there's some other advantages. We've gone from 3 antennas to 2. We have 1 transmit and 1 receive. We don't have 2 transmit antennas. And by having this delay attenuator and delay line, this programmable attenuator and delay line, we can actually make the circuit adjust to changing conditions in the environment. So how do we make it adapt to change the environment? Well, you want to adjust these values. It turns out you can't do it in the digital domain because if you're badly configured, your ADC is going to saturate. So you use a really simple measure. Just look at the RSSI of the signal. So you start transmitting. And if nobody else is transmitting, so it's just you then start tuning your circuit until you can't hear yourself transmitting anymore effectively, until the RSSI, the observed signal strength of your own signal, reaches a minimum. And you basically put a little control feedback and use this RSSI as the indicator of self-interference. And so the objective here is we want to minimize the received power when we're transmitting, assuming no one else is. And we have 2 control variables, the delay and the attenuation. And it turns out, though, what's nice is for this optimization problem is that there's just one global minimum. There are no local minima. And so you can use a simple, greedy, sort of gradient descent approach to optimize this functioning, find the optimal parameters. So I'm not going to go into the details. The second paper published, a few weeks ago gives the exact algorithm, but the basic point is that we found using the test setup that we could converge to the global minimum in about 8 to 15 iterations of the algorithm, which took about 1 millisecond. So you start transmitting. In about a millisecond, you can converge to the optimal settings. Just pretty promising. Millisecond isn't too long. So if you bring it all together, there's of course a lot more stuff I'm not going to talk about how the digital interference cancellation, all these sorts of other pieces of the puzzle. But so the idea is you just have these 2 transmit. You have 1 transmit antenna, 1 receive antenna. You use the Balin. You have the RF reference. There's control feedback to control the delay and attenuation of that. Summit, that then goes into the digital system where you can do some digital interference cancellation.
That's implemented digitally?
What is implemented digitally?
Or is that analog?
That's analog.
Control feedback. Analog or digital?
So that is analog.
Okay.
Yeah, that is analog. It's digitally controlled though.
So your simulations, the 1 millisecond, was a discrete simulation of how it steps through the analog circuit.
I'm sorry, so it is digitally programmable. Like you can send it commands, right?
No, so you said 1 millisecond and you showed steps.
Yeah.
Those steps are a trajectory of the analog circuit converging. It's not digitally stepping.
Yes.
Okay.
Yeah. No, I'm sorry. No, so that's how I was confused your question. No. So it is a digital circuit in that you are setting digital values for something, right? So it is a digital circuit, but it's dealing on an analog signal.
So you have something sampling at 2.4 gigahertz at carrier?
No, this is just the RSSI.
Oh, I'm sorry.
Searching,
Okay, it's
yeah.
just interference.
Yeah, it's just inference, yeah.
Not carrier.
Yeah.
Well, but it sounds like the Balin ends up being tuned for a particular frequency. So as a result, in this system, you don't get frequency agility. You have to be hanging out at this particular place.
Oh, so
The phase thing, you could play around the.
So you mean here where it's so we haven't dug really deeply into all the Balins that are out there and all of the possible options and exactly what the limitations are. So it's true, if this is the best Balin there is in the world and you actually wanted to operate across the entire, say, Wi-Fi band, you'd have to have multiple Balin circuits depending what channel you're on.
A variable resistor version of the Balin.
Yeah, we haven't gone that far. It's totally something to figure. Like, is it that you need multiple cancellation circuits? This matters also for like cellular systems where you have different frequencies. Yeah, like how frequency sort of unselective can we?
Do you know what would happen if you just modulated the whole signal up first into the range that it does well at?
No. Haven't gotten that far yet. Great. So you stick it all together. Well, so I said it takes about a millisecond, but what's the channel coherence time that you see? In the sense of if the channel is changing every 5 milliseconds, and you have to readjust every 5 milliseconds, then a 1 millisecond time would be bad. If it's 1 second, that's not so bad. So this is Wi-Fi, so this is a stationary node. I'm not talking about a cell phone in a car. What we saw is that if you configure the system, then this is the x-axis is time, the y-axis is the cancellation that you see. And so you configure the system, and over time the cancellation degrades as the environment changes a bit. And basically, within about a second, you see a 3 dB reduction, and you see a 6 dB reduction in about 10 seconds. What this means is that you need to tune the system maybe once a second. And so spending 1 millisecond once a second seems pretty feasible. Yeah, so you want to tune the circuit when nobody else is transmitting, and you can do things like figure out, oh wait, this is not working. Let's abort and try again.
So, but do you know that it's not working? Do you have a way?
So we have not demonstrated situations and demonstrated that it works, but I think we know how to do that because you'd see that suddenly this would stop behaving in this simple, convex way. Right? So, like you can just say, it's not, I know how this is supposed to be working. It's not working that way. Let's just try again in a moment. And so you stick it all, if you stick these things together, you take the RF cancellation, you add digital cancellation. You can get about 70 dB, since there's also the separation of the antennas, which can give you about 35 dB. What this means that is in practice, using signal inversion, we can get about 100 to 105 dB of cancellation, which means that we can do Wi-Fi. Can't do cellular. Cellular's more powerful. But who knows? Maybe we'll be able to soon. Good question. And that's in particular because of base stations. Base stations are transmitting much more powerful than 200 milliwatts. So, can build a radio that transmits and receives simultaneously. Can build a full duplex radio. So what? So we built a demo of this. We used the Warp platform, the 2 radios, OFDM reference code, 10 megahertz bandwidths, use OFDM. We modified the system to include the cancellation circuits for full duplex. And we used the standard CSMA MAC. This is basically sort of just to evaluate what's happening at the link layer. So, sorry if you know this is old schooly, but some people might not. So one big problem that you encounter in wireless networks, particularly Wi-Fi, like ad hoc networks, is something called a hidden terminal, where I have an AP and I have 2 nodes that both want to send message to the AP. The AP can hear both of them, but they can't hear each other. And what happens is N1 tries to transmit to the AP, the node on the left. N2 says, wait, I don't hear anything, I'll transmit too. It transmits, the packets both arrive at the AP simultaneously, they collide, the AP hears gibberish. And so it's called the hidden terminal because N2 is a hidden terminal to N1 and vice versa. So CSMA, the standard Media access protocol doesn't solve this. There are some more complicated protocols that can help, like RTS, CTS, but generally people don't use them because of their overhead. So this is just this basic problem you encounter in wireless LANs today. So it turns out, people have been trying to solve it for 30 years, since Aloha. So it turns out full duplex can actually solve hidden terminals. So the way it works is N1 sends a packet to the AP, and then the AP immediately starts sending a packet in response. It can be garbage, it can be a packet to N1, doesn't really matter. What matters is that N2 hears the access point transmitting this packet, and it knows to not transmit. Basically, the access point can clear the channel around it so that there aren't hidden terminals that interfere with N1's transmission. And so we evaluated this and found, just given our prototypes, you could reduce hidden terminal losses by up to 88% by using a full duplex system. And so it's not 100%, because you can imagine there's this little latency where the AP has started receiving a packet, but it's not sure it's for it yet, and so it doesn't know whether to respond. So it's not perfect, but yeah, Arjun.
Is it just the AP that's using the full duplex radio, and N1 and N2 are not unlocked?
So in this case, yeah, neither N1 nor N2 needs to be full duplex, right? Just the AP does, and you get this benefit. Now, if N1 isn't full duplex, and the AP tries to send a message back to it, and one can't hear it, because it can't receive and transmit simultaneously. So in that way, I said the AP could just send gibberish, right? It could just send some garbage packet to itself, etc. But so in this case, just the AP needs to be full duplex.
So the difference is now you manage to do the clear and run practically instead of so your AP to N1 is similar to a clear that.
Right, except that rather than a control packet which says you are clear to send for this duration, where then if that control packet, say, was lost at N2 because of a collision, N2 will then transmit. Here, it's actually you're actually occupying the channel, and so you can just by carrier sense know that the channel is busy.
But the real value should N1 is full duplex as well, and you can get useful work done.
Yeah, absolutely.
If N1's half duplex, they're jamming.
If
N1's half duplex, AP's jamming.
well,
It's sending back a packet in band.
well, so jamming in the sense of it's preventing others from snooping on N1's transmission. Some people have actually started exploiting this for security reasons. This property. N1's transmitting; it can't hear anything, right? Yeah. So.
So at the same time, you're adding here.
Yes.
You're bringing up the
Yeah, that's true. Yeah, which in a cellular system, like for doing CDMA or something, that's going to be important here for Wi-Fi that's of less concern. Like you could say that, aha, the AP is transmitting, now N2 can't receive something because of the AP's transmission, right? It's exposed, so it can accentuate the exposed terminal problem, but I think hidden terminals are a bigger issue. So this is getting to what Stefan was saying. So it also turns out, if you look at wireless access point networks today, there's this issue where Wi-Fi says every node is equal, but in terms of carrier access, where every node gets an equal chance of the channel. But in an AP network, not every node is equal, right? An AP is in some ways more important. And so one of the problems you encounter in AP networks is that the downlink throughput from the AP to all of the nodes is 1/nth of the capacity. Meanwhile, each of the uplinks also gets 1/nth, and so there's much higher uplink capacity than downlink capacity. So there's this break between what the link layer is doing and then what the network layer or higher layers want to do. So does anyone know how AP networks solve this today? Solve this problem? There's generally the AP kind of cheats. It doesn't back off normally. So you're expected to back off exponentially, and the AP doesn't. It gets itself precedent. Basically, it employs a back off. They'll often employ back off strategies which give them preference over other nodes. So they try to do that to prevent this problem, but it's sort of a hack. But if you have full duplex, right, and all of the if the terminals were full duplex, unlike before where it's just the AP, you can solve this problem where suddenly your uplink throughput is the same as your downlink throughput. Admittedly, it has to be on a particular link. You can't have some situation where one node has a huge uplink and a tiny downlink. But still, you can actually make the uplink and downlink throughput equal for an arbitrary number of clients. And so we evaluated this, and found that with half duplex, we were seeing the Jaynes fairness index of about 0.84, where the upstream capacity was much higher than the downstream capacity. Using full duplex, much closer. Right? So we can improve fairness in the wireless LAN. So that's two things we've evaluated. There are a lot of other things you could possibly do. So currently on mobile phones today, you've got all kinds of radios working in all sorts of different bands, and they interfere with one another. Right? And this is a basic coexistence problem. And so generally, if you look at phones today, what they do is they limit which radios can be active at the same time. Like I can't be operating Bluetooth and Wi-Fi and say Zigbee or something at the same time, or I'm going to say disable WiMAX when I'm doing or disable Bluetooth while I'm doing WiMAX. But if we have something like a full duplex cancellation circuit, maybe we can get all of these chips to coexist better, where we can use this self-interference cancellation such that we can be receiving LTE or WiMAX without seeing this bleed over interference from our wireless LAN transmissions. And so I gave you a couple examples of things you can do in access point networks with full duplex. There also might be things in cellular networks. So there's one student at Stanford looking to this idea of I set up a relay, and what the relay does, it relays what the cell base station says, and maybe if I had a really smart phone with some new physical layer capabilities, so the signal from the base station to the phone is going to have some kind of error, some kind of attenuation. There's also going to be that to the relay. Can the phone take those two signals and combine them? Basically have some kind of coding such that the relay, able to receive and transmit simultaneously, the phone can combine these two copies of the signal it's seeing and somehow get a better throughput from the base station. So in wired networks, we often talk about cut-through routing versus store and forward. Do you receive the entire packet before you put it out on the switch, or you just start switching it immediately upon seeing the header? So in multi-hop wireless, we've always done store and forward. You have to receive the packet, then you forward it. But if we have full duplex, we can do cut-through wireless. You can start receiving the header, and as soon as you see it's for you, you're the next hop, you can start forwarding it. It's kind of cut-through wireless routing. So one thing that people have been exploring recently is using full duplex for security. The idea is that if these two nodes have a full duplex channel between them, or even just one of them can transmit while it receives, then these two signals interfere everywhere else. The way to think of it is that the second transmitter, the second node, still creates interference, right? Still creating interference signal for the entire area, except it's creating one position itself where there isn't interference. And so in this case, there's some stuff from Dina's group, like using it for security in medical networks, right, for medical devices. But I think there's a whole bunch of different areas of potential. I couldn't really tell you sort of right now where the biggest one is. And I think that's an interesting open question. So there's a lot of potential. What are the deal breakers? So the first deal breaker, so what I mean by that is why might this not work? What would be the thing which, if this isn't solved, this is impossible, the technology, will have, although it currently already has application, will have limited future application. The first is this question of V equal A. So if I can't make the attenuation and delay across the cancellation path equal the attenuation and delay across that self-interference path, then I can't cancel my own signal. And so you need, and there's a question of the precision and the accuracy of this variable attenuator and delay line. And that's going to limit how much you can cancel. And so if it turns out that we can't, that today, the devices of today are the best you could ever do, and producing better ones would, just be exorbitantly expensive, then we might be at the limits of what full duplex can do. But if we can do better, then we can do better. So this is getting back to what Stefan asked about, frequency selectivity. Right? So right now, hey, we can do 20 megahertz wide, right? We can do a Wi-Fi channel. But if we can't get this is again a sort of a limit. Do we need multiple cancellation circuits? What's the breadth of what we can do? If it turns out that really any system you build can't do much better than this, then we've sort of hit the barrier of what is possible. But I'd like to think, this is what engineering research is about. Chances are we can do better. Finally, and this goes back to an early question, what about multipath? Where so far I've been drawing this simple picture that, my only interference is in the line of sight path from one antenna to the other, but there's multipath in these environments, especially for stuff like Wi-Fi, where the signal's bouncing off the wall, and so I'm receiving not only that one, but multiple paths of the signal. So in the design in the second paper, solve this in the digital domain, can actually handle multiple interference paths. But if some of those interference paths are really strong, like the device is against a wall, and so it's beyond the level that, say, digital interference can cancel, it might be that you need multiple cancellation circuits. And how do you tune those cancellation circuits? So for cellular systems that see maybe less of that scale of multipath, it's not as big an issue. But certainly for Wi-Fi, this could be a difficult challenge. So a lot of that in mind, where is this going to succeed? And I can only guess. So one thing that's certainly important is where capacity is ultra scarce. Right? If you're already at the limits of your capacity, the ability to receive and transmit simultaneously doubles your throughput. Now, if you're in the RF communications community, you'll say, well, but if I have two antennas, I can do MIMO. I could double my throughput. But there are situations where you can't do MIMO. Like you want to have point-to-point links, and you can't get the antenna separation that you need. Situations where you have fixed channels and bands. So if you have to operate across a really, really wide bandwidth, a huge space of frequencies, just the frequency selectivity of real hardware might make this difficult. So situations where you're working with fixed channels and bands, like cellular systems today, where it's pretty static what bands are being used, or Wi-Fi. One question is, do we have to build whole new systems? We're going to do drop-in replacements. If I give you a Wi-Fi, full-duplex Wi-Fi AP, it's going to perform better than a half-duplex Wi-Fi AP. So that's that's promising. One thing that's clear is that channel coherence time has to be, if it's smaller than the packet time, then we're in trouble. If we need to adapt the channel faster than the packets themselves are, it's going to be hard to do self-interference cancellation. So if you're talking about amazingly long packets and fast-moving cars, this might not work very well. But I guess my true answer is I'm not totally sure. I don't know. I mean, nobody expected that we would use lasers to read music in the same way. I don't really know exactly where full duplex is going to be most effective. So, in a nutshell, we can build full duplex radios. This breaks this fundamental assumption. It's been part of wireless network protocol design for 30 years. We've been able to build it for Wi-Fi. It's an open question as to how much further we can go. Can we do 1 watt? Can we do 10 watts? Can we do 100 watts? Time will tell. I talked a little bit about how full duplex could actually change wireless. Right? There's this fundamental assumption. We've thought this way for 30 years. We try to think differently. What can we do? I think we're only scratching the surface. There are some technical barriers. There are some gotchas. But my hope, and certainly my belief, is that while I don't think we're going to have 1 megawatt full duplex transmitters, I think given that this is the work of 3 or 4 graduate students over the scope of 2 years, my hope and my belief is that we have a lot further to go. Happy to take questions. Can you give me an example of such a protocol?
I can't really think of a wireless, but in wired networks, if you want to build up the lookup table for the bridge has to pass the listen and the packet passes through the LAN. So I don't know
Yeah, so for things like ARP, certainly for things like ARP tables, link, all that kind of stuff, ARP tables as well as link clarity, that's totally right.
Also, and why are some of the coding stuff relies on passively listening?
Yeah, so it's certainly, the research community has absolutely loved the idea of passive listening. What can we do with that? And so it's true, in some ways, full duplex can be contrary to that. So we could position them as at odds, but no, that's right. That's absolutely right. So, I mean, nothing is totally for free, right? So.
I don't know if you've thought about it, but would be really interesting if you think about CSI, one of the reasons that we have these sort of long back-off periods is we don't want to, we want to contend over the channel for short periods of time, but we'll send long packets. So this will enable you to actually cut back on all of that overhead in some way and talk whenever you have something to say, and if you're, if somebody else starts in the middle.
So that's right. So if you look at something like Wi-Fi today, in fact, I mean the CSMA backoffs are actually pretty short. Like the initial backoff is well below packet times just to provide some jitter, and then eventually you back off to maybe packet times. So actually, I think one of the really interesting things to me is that if you have a back channel, suddenly the receiver can start sending you channel state information. It could actually tell you like, no, you should be sending at this bit rate. Please send at this modulation. And that can be something you do dynamically. So like rather than I send you the Wi-Fi header, and while I'm sending you the Wi-Fi header, you send me something back which says, in fact, please send at this bit rate. You should dynamically in real time make that decision. The receiver has that state. There's no inference needed. So that then raises this question of if I can tell you what bit rate to send at, maybe we should transition from a packet model to a time model, where when I win carrier sends, I have a certain amount of time. I guess they're laughing, right? Good. I can now have this much time to send, and then based on the bit rate you tell me, I'm going to put more or less, more or fewer bits in there. That would be a subtly different way to structure things. Or you then actually, it might not be that you actually have TTMA, but you end up having with something like that in terms of the structure of time of the protocol.
What I was going after is you don't even need to, if you have a back channel, you can do a lot of the negotiations of who has the channel.
Yeah.
To the listening part. Negotiate that instead of scheduling. A lot of you either schedule or you just don't schedule in Wi-Fi, which wastes a lot of airtime for meetings and stuff like that.
Yeah.
I think you can do both.
You can also do things like, look, I start sending you a packet. I don't hear a response from you. That means you're not receiving it. I should terminate early. Right, so, yeah.
Your mainline cancellation, you said you're building that as an analog circuit?
Yes, it's an analog circuit.
Continuous time, or is that going to be like discrete time or sample time switching capacitors?
That's a great question. So again, EE students do this, and I'm a CS professor. So generally it's continuous time currently. But I mean, one of the tricks here is we are using it. This is very similar to how balins have been used before. You just think like cancellation circuits, even on old school phones, all that kind of stuff. And this is for a different domain. It's like of the frequencies we're talking about. And I think it's an open question whether or not we do want to maybe use balins slightly differently and build them differently than we have been. I mean, it's a pretty simple circuit, but I don't know if that answers your question. Sort of, no. Okay. Yeah. The antenna? I mean, currently we've been using standard, omnidirectional antennas. Whether or not there'd be something in antenna design that could improve this, that's an interesting question. Interesting question, but. Not really. Yeah.
These are really dumb questions.
Then that means it probably isn't, right?
So, is there a reason why this would not be possible to do in the wiretap?
You mean just cancel what?
Full duplex over
Sure. I mean, yeah. I mean, cancel what I'm. So I think many wired systems do this now. Like we were sort of mentioning, like the phone network, right?
Well, by and large, we don't for digital. We have a separate, like full-duplex Ethernet. We use duplex.
Oh, I see what you're saying.
Why can't I double my bandwidth? The same. I mean, if this works, why is it limited to the wireless domain? Why can't I just do the wired domain, turn it on, and 2x bandwidth everywhere just with a little circuit?
That's a great question. So you said it's a dumb question, but it's not, right? So I don't know. Good question. Does anyone here know? No. Okay. I will ask the yeah. So in this particular case for this design, you do double the transmit power coming out of the TX front end.
And then 10G and 40G cable, or 10G cables are limited by power, basically, like the bandwidth.
But it turns out that that's so what I show where you do minus T plus T. So there are bail-ins that are not tapped at the center, where like you get, rather than minus T plus T, you get 0.9 plus 0.9 T and minus 0.1 T, right? You can do a tap that's not centered. Exactly whether that's going to have some frequency selectivity or some other issues, I don't know. But that's something to explore.
Well, I have a digital signal.
Yeah.
Would the advantage, let's say, not quite the same frequency, but offsetting the transmit and receive LOs intentionally, and then looking for, let's say, minimizing the intermodulation distortion of products that you get, let's say with your bail-in technique. Because right now, like ideally, they would be at exactly the same frequency. Let's offset them by 300 parts per million intentionally, and look for the intermodulation and minimize that.
Sure. That's a great question. And part of the trick now is we are constrained with the hardware platforms that we've got, right? What we're playing with, and there are a bunch of. Yeah, that's a great question. Because that might be possible, right?
You just see that you have this 1 hertz, 10 hertz beat frequency that's
Yeah.
easy to detect, easy to minimize.
Mm-hmm. Yeah, that's true. Although if it's at that slow a beat, right, then, currently the control circuit for using just RSSI, it's very much like, hey, we've got the hardware to do this. It's pretty simple, and it just works. This is this simple thing which all wireless chipsets have, and it operates across a range greater than when you're actually in the digital sample range. No, that's a great question. So, all right, thanks.
Thanks a lot, Bill.
Good.